Greetings, future leaders of America, and welcome to our nice little review on square roots. Hopefully, you guys remember a lot of stuff about square roots from your time back in Algebra 1 as well as when you were in middle school. We're going to be starting this unit off by taking a look at square roots, and we're going to need to know a lot of these concepts to kind of move forward within the course. So we thought it would be of interest of everybody to go through and do a little review, make sure we're all on the same page, and make sure we're all using the appropriate vocabulary. So the first thing that we're going to go through and do is look at the definition of a square root. So the definition of a square root is that the square root of a number x is a value that when multiplied by itself gives the number x. It's kind of a weird roundabout way to go through and define a square root, but it works. The example we're going to use to highlight this is that 4 times 4 is equivalent to 16. And because 4 and 4 are the exact same value and they've been multiplied together, so the square root of 16 must be 4. Okay. Also, just to make sure that we all are aware of what different things are called, the radicand. Okay, the radicand is the symbol that we use to represent a square root. And the radicand, you might have had other teachers or math classes refer to it as the house or the root box or something like that. But we are going to exclusively be referring to it by its proper name as the radicand. Okay, so some radicals are expressed in what we call simplest form. So we have 3 examples here that are all expressed in simplest form. We have the square root of 21, we have the square root of 3, and we have the square root of 10. The reason that those are said to be expressed in simplest form is that there is no alternate way that I can write the value for the square root of 21 that uses values smaller than 21. Okay, 21 is what we call a composite number. It has multiple factors. However, none of those factors ever repeat themselves. So we can't simplify that radical anymore. The square root of 3 in the middle, well, that one's a prime number, so it doesn't have any factors besides 1 in itself, so it has no repeating factors. With 10, 10 is a lot like 21. It's a composite number. It does have multiple factors, but it doesn't have any factors that repeat. And when they cannot be broken down any further, then we call them expressed in simplest form. Some radicals, though, can be rewritten using smaller values. This process is called simplifying. You might also hear it called reducing, but we're just going to try and stick with simplifying a radical. So, for example, if we look at the square root of 18, the square root of 18 is equal to 3 times the square root of 2. Well, how is that in simplest form? Well, 18 is a big number, and both 3 and 2 are smaller than it. Later on, when we start doing more with radicals and values that are inside the radicand, you might be multiplying something by what's inside the radical. Well, would you rather multiply by 18 or by 2? One of those you can probably do in your head. The other one you probably need a calculator for. So it actually makes successive steps easier when we go and express those radicals in simplest form. Okay, hopefully we remember a process for going through and doing that. Okay, that process involves looking at what all of the factors are of a particular value. However, in this class, we are most definitely not, I repeat, not going to be making factor trees. So if you looked at the square root of 18 and thought right to yourself, ooh, yay, fun, factor trees, not doing that. Okay, we're going to start using some properties to go and solve that. Okay, so your days of going and saying, oh, well, I have the number 18 and I'm going to make some factor trees and I'm going to put something here and something here and then I'm going to make some more factor trees and put something here and something here and then I'm going to arbitrarily draw different geometric shapes around certain things that mean other. No, not doing that anymore. What we are going to be doing is starting to use properties of radicals. So on the next slide, we have two properties that we're going to be going and illustrating here. Okay, the first property is the product property. Okay, hopefully we all remember that product is really just the fancy mathematical word for when things get multiplied together. So if we look at the example with variables in it, we have this square root of AB. Well, hopefully everyone remembers that in algebra, adjacency implies multiplication. So instead of writing this square root of a times b under a single radical, we can actually write it as the square root of a multiplied by the square root of b. Okay, that could be really useful when we're trying to do something like simplify. So if we go over and look at the numerical example, we started off with the square root of 50. Well, is there a way that I could rewrite the number 50 that uses a perfect square as a factor? And there is. 50 can be factored into a perfect square factor of 25 and then a prime factor of 2. So could we take that one step further and even go and simplify it? We absolutely could. So we could go and express this as the square root of 25, which is 5 times the square root of 2. This is a much smaller value for me to contend with than the square root of 50. So that's why we say it's expressed in simplest form. We also have what we call the quotient property. Okay, in the quotient property, hopefully everybody remembers that quotient is just the fancy math word for division. So we see that there is some sort of division that is existing underneath the radical. Well, just like what we can do for multiplication, if we're following the quotient property, the square root of a quotient or a rational value that's expressed as a fraction could also be written as the square root of the numerator over the square root of the denominator. Okay, so that's going to come into play when we look at simplifying fractions or rational expressions that are underneath the radical. So for example, we've got the square root of 25 over 9. Well, 25 over 9 is going to give you some random decimal. Okay, I'm going to go ahead and say it right now for Algebra 2. Decimals are the devil, and fractions are our friends. So we want to keep things as much fractions and as far away from decimals as possible. So I don't want to be taking the square root of some weirdo decimal. I want to go through and see, hey, can I kind of split this up a little bit? So I've got maybe the square root of 25 over the square root of 9. Okay, so I've got those two. And if I was to continue trying to simplify that, well, what would I end up with? Well, do we know what the square root of 25 is? Sure, it's 5. Do I know what the square root of 9 is? Sure, it's 3. That's a whole lot easier than going and trying to convert 25 over 9 into some decimal and then take the square root of it and then go through and rewrite it as an improper fraction like we have here. Okay. Also, we're going to be using a lot of variables and radicals, so there's just a couple of relationships that I want to make sure that we all remember from previous math classes. The most important of which is the fact that the square root of x squared equals x. That's actually the definition of what a square root is, but we also need to recognize that the radicand is a mathematical operator. It tells us to do something mathematical. The exponent, 2, is also an operator. It tells us to do something mathematical. But this radical and that exponent of 2 actually tell each other to do the opposite thing from what they are. So they undo one another. Those are what we call inverse operations. All right? So we need to remember that the square root of x squared will always equal x. So how can we apply that along with maybe one or both of the properties that we've already talked about? Well, we're going to go through and look at, say, the square root of x cubed. Well, the square root of x cubed could be rewritten using smaller exponents, so smaller numbers. So we could write it as the square root of x squared times x. Then we could use the product property and say that that's the square root of x squared times the square root of x. But what is the square root of x squared? X. What's left over? Root x. So the square root of x cubed expressed in its most simple form is just x times root x. Okay, it may not look or seem simpler at this point and in this context, but as we work our way through the course material, it's going to be a whole lot easier to deal with, right? So let's take a look at a few examples of how we can go through and simplify some radicals, okay? So to start off with, we're going to look at two examples and work our way through how to do each one of them. One thing that we need to keep in mind is that when we're trying to simplify a radical, we always want to try and identify what the perfect square factors are before we even attempt to kind of factor it. So what are all of your perfect square factors that aren't 1? Well, you've got 4, you've got 9, you've got 16, you've got 25, you've got 36, you've got 49, and you could keep going, but I'm going to run out of space if I write any more than that. So all of those are our perfect square factors. So what we're really trying to do is we're trying to see, if I think about how to factor either one of these problems, which one of these perfect square factors is going to be the best one to go and use. So when I think about the number 45, is 45 divisible by 4? Not really. Is 45 divisible by 9? It is. 9 times 5 is 45. So I'm going to use that. So I'm going to say that the square root of 45 is actually equivalent to the square root of 9 times 5. So using the product property, that means that it's really the square root of 9 times the square root of 5. Well, I happen to know for a fact that the square root of 9 is 3. So this is 3 times the square root of 5. 5 is a prime number. It cannot be simplified any further. So this has been expressed in simplest form. Both the number 3 and the number 5 are smaller than 45. Win-win. If I go and take a look at example 2, we've got the square root of 108x cubed. So first, I'm going to kind of go and separate this up a little bit, where I'm going to go and do the number here, and then I'm going to do the variable kind of separate. So I'm going to go ahead and split this problem up. So I'm going to say that this is the same thing as the square root of 108, and I'm going to be multiplying that by the square root of x cubed. Okay, so let's just try and simplify the 108 first. When we're trying to go and see what factors it has that are perfect squares, most of the time we really want to start with the largest ones because that's going to make less work overall for us to do. I didn't do that with 45 because it's smaller than most of the numbers that are our perfect squares, but 108 is larger than all of these. So I could go check and see if it's divisible by any of those perfect squares, but I'm going to start at the larger one. So first, let's start at, say, 49. So if we go and take a calculator, or even if you just know this, if you take 108 and divide it by 49, you do not get a whole number, which means it's not divisible. So that one doesn't work. We could take 108 and divide it by 36 to see if that is a factor. 108 divided by 36 gives you 3. So that one is divisible, so it must be a factor. So this 108 could really be written as the square roots of 36 times the square root of 3. And then over on the other side with my x squared, I could really say that that's the same thing as times the square root of x squared times the square root of x. So now I can go and simplify this, right? The square root of 36, I happen to know, is 6 times the square root of 3. The square root of x squared, I happen to know, is x. And then the square root of x can't be simplified, so it stays that way. So now I just need to go and combine all of the things that are outside the radical together and all the things that are inside the radical together. Again, I'm using some of those properties. So I have 6 and I have x that belong outside of the radical, and I'm going to be multiplying that by 3x inside of the radical. And that's going to represent my simplified form. Okay? So if we go take a look at the last two really quickly, these are going to involve quotients. So we're going to be using the quotient property for these two. All right. So Looking at example 1, we're going to say the square root of 5y over 16 should really be expressed as the square root of 5y over the square root of 16. Well, 5y represents a product, but 5 is prime, and so is y. So I can't really simplify anything there. So the numerator is going to stay root 5y. The denominator, on the other hand, I know that the square root of 16 is the number 4. Okay, so that has been simplified as much as I can. Over on the other side, we've got the square root of 81 over the square root of 169. We want to go and split this up using the quotient property. So we're going to say the square root of 81 over the square root of 169. Now, some of you probably are looking at the square root of 81 and thinking, yeah, that's definitely 9. Okay. You may then look at 169 and say, I don't really know. If you use your calculator to go and figure out what the square root of 169 is, that's totally okay, especially if it's a perfect square. I just happen to know from memorization that the square root of 169 is 13, which kind of makes sense because it's a little bit more than 144, but a little bit less than 225. So it's got to kind of fit in between all that stuff. So that's going to be the square root of 9, or sorry, that's going to be equal to 9 over 13, and there are no square roots. All right, so you should be good to go to work on the review assignments that you've been given. Just please make sure that every time you're trying to express a radical in simplest form, you're always trying to factor out the perfect squares and not just the first number that pops into your head. All right, so good luck with that, and make sure to ask me any questions if you have them.